Part B, efficient polynomial evaluation. B.1, evaluate the polynomials. All right. Let's look at the problem. Our computing problem number 2, evaluate a polynomial. Question. We consider data. So the given data is a polynomial. To consider a polynomial, what we should have, the input data. The coefficients should be given. All right. And we also need to know the value of the variable x. All right. Question. How to evaluate polynomial p of x efficiently? Here, this word is very important. Efficiently. Yeah. From this question, you can see in our algorithm class, when we solve a computing problem, first we need to make sure we find the correct answer, but that's not enough. After that, you also need to make sure your solution is efficient. From this question, we want to understand this concept, efficiency concept, well. All right. So here, let me give you the reference of this topic from our textbook. It is in section 6.5. So why I pick a topic from some late chapter? There are two reasons. First, we need to do some preparation for our first programming project. And I feel this topic is very interesting for our first programming project. Okay. First, it is not very hard. So we can understand the idea easily with our knowledge. All right. Second, we can show this efficiency concept. We can learn a lot of things about efficiency of algorithms. All right. So let's look at the question. First try. When we start at the beginning, because we do not have a good idea how to solve the problem, right? So for our first try, we only want to see how to solve it correctly, all right? So in our first try, we want to see how to solve it correctly. Not efficiently, okay? Because efficiently, our second round. First round, find a solution. Find a correct solution. Second round, find an efficient solution. All right. So here we just use a straightforward algorithm. All right. Let's look at the basic operations. If you look at the polynomial, the basic operations, only two basic operations, additions and multiplications. So let's work on term by term in this polynomial. There are many terms. So let's look at one of the terms. And we use a representative of the term, a general term, And we use this general term as a representative case study. Okay? Yeah. We want to count the number of multiplications we need to calculate this one term in the polynomial. Yeah. How to find the answer. Yeah. Yeah. So here it is a small computing problem, right? Yeah. But think about, can you quickly find the answer? How many multiplications do we need to calculate this general term? Yeah. Try a little bit. Yeah. All right. Yeah. Some of you may not be able to find the answer quickly. Think about it. Why? Because this k is unknown, right? Yeah. Yeah. This k could be 1, could be 3, could be 100, could be 1,000. Yeah. Yeah. So many people, when they see this kind of uncertainty, yeah, the value of k is uncertain. Yeah. So many people, when they encounter some uncertainty, they do not know how to handle. Yeah. All right. So here, yeah, our first problem strategy. Let me introduce the first problem-solving strategy here. Yeah. All right. The strategy. Yeah. Here we do the counting, right? Yeah. So this step we do the counting. When we do the counting here, yeah, some simple strategy we need to apply here. So what strategy? Do experiments. Let me write a little more. Do experiments for simple cases. Okay? When we do experiments, it's better we consider the simple cases first. That's easy. Yeah. So when we start, we want to work on the easy cases. Yeah. All right. So let's do some work. Yeah. First, k equals 1. Yeah. Let's count the number of multiplications we need when we calculate this term. a1 times x to the first, just x. Yeah. How many multiplications? Yeah. It's very easy. You can see we only need one multiplication here. All right. Yeah. So let's do another experiment. a2 times x squared. X squared. Yeah. Yeah. So you need one more multiplication when you calculate x squared. Yeah. a2 multiplication, a2 times x squared, you need a 1, but x squared you need another 1. Yeah. Yeah. So total you need 2 multiplications. After these 2 simple experiments, can you see how many multiplications do we need in this general case? Can you see certain rule, some interesting special rule you can observe from the simple experiments? See, yeah. So our conclusion is we need k multiplications to calculate this general term. Yeah. So here you can see some kind of problem-solving strategy, simple but effective strategy we have applied to solve this simple computing problem. Yeah. Later we will apply this strategy many, many times. Yeah. All right. Next. Yeah. Let's think about, is your algorithm efficient? We don't know, right? No. After we find the answer, but if you want to see if our straightforward, here we do the straightforward method. If our straightforward method is efficient or not, we don't know. The reason is because we need to do comparisons, right? When we want to see if it is efficient, we need to have, at least we have more than one algorithms so that we can do the comparison. But here we only know one way, right? Straightforward way, one way. So we don't know if it is efficient or not. Yeah. All right. Yeah. Yeah. But there is another thing. Yeah. When you talk about efficiency of some algorithm, how do you measure it? Yeah. So here, we want to study the efficiency. Yeah. And the question, how do we study the efficiency, right? Yeah. So we may need some performance number to help us measure the efficiency. So here there is a measure problem. How to measure the efficiency? Yeah. So we need to consider this question. Yeah. All right. Performance number, yeah. So when you think about to find appropriate number to measure the efficiency, yeah. So you may have several ways, right? Yeah. So here, when we want to find an appropriate way, yeah. First we want to avoid, subjective way. Yeah. Because when people talk about efficient or not, most of the time it is subjective, right? Yeah. If the efficiency question is subjective, then it's not good. Different people may have different ideas on the efficiency issue. Yeah. So we want to make it objective. Yeah. So we need some appropriate number to measure the efficiency to avoid the subjective understanding. Yeah. All right. So how to do that? Yeah. So we will do that discussion later. Yeah. All right. Next question. Are we satisfied with this solution? Yeah. So this, k multiplications to calculate this general term. Are we satisfied? If we cannot do better, then we have to take it, right? Yeah. Because we don't know how to do better than this answer. This is our first try. It's possible we can find a better solution, but at this point, we do not know how to get a better solution, right? Yeah. At least we need to try it, right? Can we do a little better? Yeah. So here, we need to do some experiment. Yeah. So here, we want to consider the simplest case. Yeah. All right. To calculate x to the kth power, but we want to work on some simple case. Yeah. All right. Yeah. So this is we call it monomial. Yeah. Let's do a relatively simple calculation of a monomial. Yeah. Look at this one. X to the fourth, this monomial. This monomial, if we use our current method, the current method here, yeah, how many multiplications do we need? Yeah. You can see in this monomial, there is no AK part, right? Yeah. AK coefficient becomes 1. Yeah. When AK is 1, you don't have that multiplication, right? You don't need to do multiplication 1 times x to the k. Yeah. So you can save one multiplication. Yeah. Yeah. All right. Then, to calculate this monomial, we need 3 multiplications, right? Not 4. Yeah. Not 4. Because we can save one multiplication here, yeah, on that AK part. Yeah. To calculate x to the 4th, we need to do multiplication 3 times. Let's say x times x times x times x. 3 times, right? 3 dots, 3 multiplications. Yeah? So that's our current method. Yeah. Now the question, is it possible we can improve our method? So we want to reduce the number of multiplication. Can we do a little better here? Yeah. Let's try. Yeah. All right. Let's do our first multiplication. X times x equals x squared. That's our first multiplication. Okay? All right. After that, when we do our second multiplication, this time, we do it in a special way. X squared times x squared. Yeah. All right? X squared times itself. Not x. No. X squared times itself, we get x to the 4th. Yeah, that's our destination, right? Yeah. Yeah. If we do in this way, you can see, yeah, just a minute. Yeah. If we do in this way, you can see we need 2 multiplications instead of 3. So there is an improvement from 3 multiplications to 2 multiplications. Yeah. So from this simple example, you can see it is possible to get a better solution. A better solution than our straightforward method. Yeah. There is a hope. Yeah. There is a hope. Okay? Yeah. So if we can find a smart way, we can do better. Yeah. So that's the conclusion. Okay? All right. Next, let's continue. We along this direction, we want to find a better solution. Yeah. All right. Now this time, yeah, we work on a better algorithm because we see the hope. Okay, yeah, we see the hope. We want to find a better algorithm. Okay, all right. Here, to do better, we have the problem. We do not have a lot of experience here at this point because we do not have a lot of background in our algorithm. Yeah. All right. So, how to do better? Yeah. All right. The first, in the previous slide, when we do the straightforward method, so later we will call it the brute force method. Yeah. Yeah. So it is very common in problem solving. The first time when you want to solve a given computing problem, you do not have any idea. Yeah. That's very common. Yeah. Then many people just apply the brute force method as the first try. Yeah. After that, then try different ways to improve it. Here we take the same approach. Our first try is the brute force method. Yeah. After that, yeah, based on our another simple experiment. Yeah. We are encouraged that we can do better. Yeah. So now we have the hope we can do better. Yeah. So the question is how to do it much better. That's our next goal. We want to improve it as much as we can. Yeah. All right. So that's here. When you look at the polynomial, it only contains addition, multiplication operation. These two operations. Okay. Yeah. Yeah. And the next question is, when we work on these additions and multiplications, how much room do we have to find the solution differently? Yeah. How much room do we have to manipulate these additions and multiplications to get a different counting result? Yeah. Because here we do counting, right? So here we do counting. We want to count the number of additions and the number of multiplications. Yeah. All right? Yeah. All right. Yeah. The room is here, the order. Order. Because when you apply additions and multiplications, what order do you use? Yeah. You have different ways, different orders to take to apply the additions or multiplications, right? Yeah. Yeah. If you recall our previous method, that's a different order. Yeah. So here, yeah, to let you see that order, importance of the order information. Yeah. So let me use the previous example to show you. The first method, we do multiplication in this order. Okay? Yeah. This order. 1, 2, 3, 4, this order. Okay? All right. The second way, we can do better. X, the first one. Okay? All right. For the second one, the second operand here, we do not need to do multiplication. We just copy, yeah? Because the first parenthesis, first pair of parentheses, we already have the value, right? X squared value. So we just copy the x squared value. Then we do another multiplication. Think about that. How different it is. Yeah. All right? Yeah. So that's the, yeah. Not just order. Here you can see. Yeah. So we take different order, but here, look at this step. This step is actually more than the order, right? More than the order. So here, later, we will call it. So this step, we call it reuse the resource. Reuse the resource. Reuse the resource. What's that? Here, the value in the first pair of parentheses, after we find its result, it becomes the resource. Then, in the second pair of parentheses, we reuse the resource from the first pair of parentheses. This idea is very important. Okay, reuse the resource. Yeah. Other than the order information, yeah, so we have the freedom to choose different order to evaluate the polynomial. But other than that, another important idea we can take advantage. That's this reuse the resource idea. Okay? Yeah? Yeah. All right. Yeah. Let's continue. Yeah. All right. Yeah. Yeah. So we have freedom to try different orders. Yeah. But at the same time, we want to reuse the resource. Okay, all right? Yeah. Then, next question. Yeah. Because we need to measure efficiency. So for this question, we want to measure the efficiency of the algorithm. Okay, how to measure? Yeah, the first option, using execution time to measure. Yeah, we clock it. Yeah. So when you run the program, we calculate the execution time. Yeah. So that's the straightforward way. Yeah. But this way, yeah, the good thing is this way is objective, right? Yeah, yeah, yeah. It's objective. Yeah. But there is a problem, a serious problem. It's unstable. This method is not quite stable. Yeah. How do you see unstable? Yeah. Because if when you run a program, here let's imagine we write a program to implement our algorithm. Yeah. But when you run your program, what machine do you use? You can use some fast machine, supercomputer, let's say, or a powerful server. Yeah. So, a lot of computing power. Think about, okay, multiprocessor, parallel computers. Yeah. So you use a lot of computing resource. But another possibility, you use some low-end computer. Yeah. So then the execution time will be different. Yeah. So that's the first special case. It is unstable. Another case, unstable, because different programmers can implement the same algorithm differently, right? Yeah. Some experienced programmers, so they know how to write code in an efficient way. Yeah. But if the programmers do not have a lot of experience, then the implementation could be relatively slower, right? Yeah. So from the software implementation point of view, it could be unstable. Yeah. So this measure our conclusion. Yeah. It is unstable. That means it's not a good solution, not a good option for the measurement of the efficiency. So, and we want to find a stable measure. The stable measure means no matter what kind of machines you use, powerful, slower, no matter your implementation details, the measure should be this. You use the same number. Okay? From hardware difference, from the software difference, it doesn't matter. Yeah. So your measurement is very stable. The same number. Okay? All right? Yeah. So that's the ideal measurement. All right. How to measure efficiency? Yeah. Using, So now, our final decision. using number of additions and a number of multiplications as the efficiency measurement here. Here you can number, counting number, yeah. Because when you use the counting number as the efficiency measurement, it is stable. Yeah. Fast machine, slower machine, same counting number. Okay? Fast implementation, slower implementation, same counting number. Yeah. All right. So that's the next step. We will use these two counting numbers. Okay? Yeah. All right? Yeah. But there is another problem. When you use these two counting numbers, because at the end, we only want to use one measurement, right? Yeah. Not two measurements. Yeah. At the end, we want to use one number to represent our efficiency measurement, not two numbers. But your additions, multiplications, they are different operations. Different operations. Yeah. So that means it's hard to put them together, right? Yeah. It's not a fair way to add these two numbers together. For example, you have 3 multiplications, you have 5 additions. You cannot just use 8. 3 plus 5, you get a number 8. You cannot say we use 8 operations. Because an addition and a multiplication, they are quite different. When we run these two operations, the execution times for these two operations are quite different. We cannot simply add up their corresponding counting numbers. So we need to solve that problem. The counting numbers for different operations, that problem. Yeah. All right. Yeah. How to choose a fair way so that we can use one counting number to cover both operations. Yeah. Here we need to make some assumptions, reasonable assumptions, fair assumptions. Yeah. So what kind of assumptions we want to make here? Yeah. Yeah. Because here there is some difference we want to, try to bridge the difference between addition operation and a multiplication operation. Yeah. All right. We assume each addition takes 1 unit of time in computer CPU. Yeah. CPU. Yeah. We know it is very fast to do one addition in a modern CPU. Very fast. Yeah. Fast give you some idea in the category of nanosecond. Nanosecond. Nanosecond we know 10 to the negative 9 second. 1 billionth of a second. That fast. In that category. Okay? Yeah. Small number of nanoseconds. Yeah. 1 or 2. Yeah. Between 1 and 2. That fast. In a modern CPU, yeah, people can do that fast for one addition. Okay? All right? So here, the explicit time is not important. We just treat that time 1 unit of time. Then, how about multiplication? So for multiplication, in our assumption, in CPU, one multiplication operation in CPU takes approximately 10 times of that of an addition. 1 to 10 ratio. Yeah. So in the real world situation, the ratio between the execution time for one addition and the execution time for one multiplication, approximately 1 to 10 ratio. Yeah. Here for simplicity, so we, assume that relationship. Yeah. With this assumption, we can end up with some fair measurement. Remember, we want to use one counting number to cover both operations in a fair way, right? Yeah, that's the goal. Yeah. All right. Next, let us do the counting. Yeah. That's the step for this step. Estimate the cost. Estimate the computation cost. B.2 topic. Okay. All right. Yeah. Now, we split our original problem into a few subproblems. The first subproblem, count the number of additions. Do the counting on additions. Okay? All right. Yeah. Let's try it. Yeah. So this time, in order to calculate this polynomial in a straightforward way, in a brute force way, brute force method, how many additions do we need? Yeah. Yeah. So here, yeah, let's practice our problem solving skill a little bit. Yeah. Strategy. Yeah. Recall the strategy. Yeah. We apply some strategy in the previous slide, right? Yeah. Yeah. Here, we do the same thing. Yeah. All right. So here, there is another strategy. Yeah. Because here, work on the easier parts first. That's the strategy. Yeah, so what's the easier part? Yeah. 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 Right. Here, because when you look at the expression here, there is some uncertain part. So this part, ellipsis. Yeah. So this part, uncertain, right? How many terms are there? We get lost, right? Think about it. We get lost. When we do the counting, when we count the number of additions, we need to go through this part, this uncertain part. Yeah. So that uncertain part, yeah, make it hard to keep track of the terms. Okay? Yeah. When we have that problem, the question, how do we keep track of the data? Yeah. Yeah. Here. Okay? All right. So we need some special method to help us keep track of the data. Okay? All right. How to find an effective way to keep track of those invisible terms. Yeah. So here, we need some strategy to help us keep track of those missing terms, invisible terms. Yeah. All right. Here, let me introduce a simple technique, counting technique. Counting. Here we do the counting, right? So we count the number of additions. Yeah. So there is some effective, simple counting technique here. What's that? We call it counting by reference. We need to choose appropriate reference numbers, reference objects. When we do the counting, we use certain reference objects to help us do the counting. Let me describe the idea of this method. All right. The essence of this method we try to discover one-to-one correspondence between two mathematical objects when we do the counting. Yeah. What's that? Yeah. So let me use a simple diagram to show you the idea. Yeah. All right. So in this diagram, we have object 1 and object 2. Yeah. Certain mathematical objects. Here I use the abstract way first. Later, I will use this model, so this method, to show you how to count the number of additions in our current problem. Yeah. All right. So between these two objects, we want to discover some one-to-one correspondence. Yeah. That step is critical. Yeah. After that, then we can do the counting. Yeah. Because our goal, we want to count the number of first object, mathematical objects. But due to some reason, it is hard to count the number of object 1. Due to some reason, what reason? This reason. Okay? Uncertainty here. Uncertainty here. Yeah. Due to that reason, we feel it's hard to count the number of object 1 directly. Yeah. Yeah. Then we move to object 2, because if we have one-to-one correspondence, this relationship is important. It must be 1-to-1. Okay? Not 2-to-1. Okay? Yeah. 2 object 1 correspond to 1 object 2. That's not good. Okay? Not a 1-to-2. Not good. 1 object 1 corresponds to 2 object 2. That's not good. So it must be 1-to-1 correspondence. Okay? All right. Then we know the number of object 1 should be the same as the number of object 2. Yeah. These two numbers should be the same. Yeah. Why these two numbers are the same? Because 1-to-1 correspondence. Okay? 1-to-1. Object 1, you have certain number of object 1. Then you have certain number of object 2, but you have 1-to-1 correspondence. 1, 1, always 1-to-1. Okay? Yeah. Always 1-to-1. Can you say the number of objects in these two sets are the same? Yeah. In the set theory, we have this result, simple result. Okay? All right. Yeah. Since they have the same counting numbers, how about we just count the number of object 2 directly? Because when we count number of object 2, due to its special property, it is much easier to count the number of object 2. So we can find the counting number easily when we switch to counting number of object 2. Okay? Yeah. After we get that counting number, then we make our conclusion. The number of object 1 is the same as this number. The counting number we derived from counting the number of object 2. That's the idea. That's this counting by reference idea. Okay? So we use object 2 as the reference objects for object 1. Now let's, apply this method on our current problem. Okay? Yeah. Let's count the number of additions. Yeah. Object 1, a plus sign. Yeah. A plus sign, we treat it as a mathematical object. 1 plus sign corresponds to 1 addition. Right? Yeah. to count the number of additions in the given polynomial, that's the same as counting number of plus signs in this polynomial, the formula of this polynomial. Yeah. So the first object 1, yeah, plus sign. Then, what's the second object? Object 2, a subscript. Yeah. Yeah. So here, let me erase. Yeah. Subscript. Okay. All right. For the coefficients, all these a coefficients, there is a subscript, right? Yeah. Subscript. Subscript. Okay. All right. Then we need to establish some one-to-one correspondence between these two types of objects. Okay. Yeah. So how to do the one-to-one correspondence? Yeah. The first plus sign, we make it correspond to this subscript. A1, the subscript of A1 coefficient, not A0. Yeah. A0 we skip. Okay? We skip A0. Why we skip? Because in front of A0 there is no plus sign. Okay? There is no plus sign before this A0 coefficient number. Then we don't need it. So in our one-to-one correspondence, we can exclude this A0 coefficient. Okay, all right. So the first plus sign corresponds to this A1, the subscript of A1. Yeah. Second, and so on. The last one corresponds to the subscript of AN. Is that one-to-one correspondence? Yes, it is one-to-one correspondence. Okay, all right. Then we can do the counting. Yeah, we can do the counting because this time counting subscripts much easier, right? Yeah. So let's look at all the subscripts. 1, 2, 3, all the way. The last one, n. When we do the counting, number of subscripts in this set, how many? Okay, it is much easier. So we can see the number of subscripts, n. N. See? Yeah. Then we go back to our goal. We want to count the number of plus signs. So our conclusion is there are n additions in this polynomial. When we apply the brute force method, there are n additions. All right? Yeah. So that's this counting by reference method. Yeah. All right. So let's continue. Yeah. Yeah. All right. Yeah. So I explained. Yeah. Yeah. Why we skip the first coefficient. Yeah. All right. Yeah. So the final answer. We need n units of time. Yeah. Because based on our assumption, one addition. To calculate one addition, we need 1 unit of time. Now we need to calculate n additions, so we need n units of time. Okay, all right? Yeah. Next, subproblem number 2. This time, we need to calculate the number of multiplications. Yeah. All right. Yeah. Now, let's do the counting. Yeah. Still, let us count the number of multiplications for one general term. We did it before, right? Yeah. Our answer is for the for the brute force method, we need a k multiplications. Yeah. All right. Yeah. Then, because we need to accumulate all those numbers, right? Yeah, for all the terms. Yeah. For all the terms. Yeah. All right. Yeah. Here there are n plus 1 terms. Yeah. If you look at the terms, there are n plus 1 terms. Yeah, but for the first term, no multiplication is needed, right? Yeah. For A0, the first term, we do not need to do any multiplication. Yeah. So starting from the second term, then we need to do multiplications. Yeah. here, let me do a chart. Yeah. To calculate A1x, we need 1 multiplications. Remember, yeah, the k, yeah, for different k numbers, the corresponding number of multiplications the same as that k number. Okay? Yeah. All the way, yeah. So we add up these numbers from 1, consecutive integers from 1 through n. Yeah. And we have a formula. Yeah. So here, let's recall. The summation formula for the first n consecutive positive integers, yeah. Yeah. From discrete math. Yeah. From the discrete math, we have this formula. 1/2 times n plus 1. Yeah. So the answer is this number of multiplications. Yeah. Yeah. After that, because we need to convert it based on our assumptions. We need to convert it to number of time units, right? Yeah, here, this step. Yeah. So some students, so they feel strange. Yeah, because here we want to consider the total calculation cost from additions and multiplications. So we need to use the time units, the certain number of time units to estimate the total cost, computation cost. Yeah. So for that reason, so this number, the number of multiplications, we need to go another step forward. So that is converted to the number of time units based on our assumptions. Yeah. So our assumption here, remember, the total number of time units. Yeah. So we completed this step, but the next step, for this many multiplication, remember, 1 multiplication corresponds to 10 units, right? That's our reasonable assumptions. Yeah. 1 to 10 ratio. Yeah. So here, assume each multiplication, we need to use 10 time units. Yeah. This many multiplications, so we need to multiply by 10, right? To get the total number of units for the multiplications, we need to multiply this number by 10. Yeah. All right? So that's 5n times n plus 1 time units. Yeah. All right. So the conclusion, yeah, the total number of time units from addition part, the first term from addition part, the second term from multiplication part. Yeah. Adding together, the total is 5n squared plus 6n. So that means if we apply the brute force method to calculate this polynomial, we need this many time units to find the answer. And this is our efficiency measurement. So this number is our efficiency measurement. The idea, the basic idea here. Okay, all right. Next, we want to see if it is good one or bad one. Yeah. Good or not. Yeah. That's important. Yeah. Because the next step, we want to improve our algorithm. So we need to get some idea how to improve it. How to do it in the right way. So that's the objective of our next step. Yeah. All right. The question, how to reduce this number? Okay, yeah. Find a, smart way to reduce this efficiency number. Yeah. All right. improvement strategy. Here we need to consider another problem-solving strategy. Here you can see in this class, when we do the problem solving, we need to apply various strategies. Or another strategy consideration here. Okay, all right. Here, if we look at this question from some high-level way, okay, yeah, global way, yeah, overview, okay, yeah. So there are two parts to be improved on. Yeah. If you look at the entire calculation, there are two basic parts. Yeah. What two parts? Addition part and the multiplication part. Okay. Yeah. So these two parts are quite different. Yeah. Now, let's compare these two parts. Yeah. Which part should we focus on? Yeah. Because we want to do it in the right way. Yeah. How do you know you do it in the right way? So here, let's do some analysis to see what is the right way to do it. Yeah. Here, let me draw a diagram. Okay. Yeah. This big circle represents the total number of time units to be used in our calculation. And it contains two parts. Yeah. One part, this part, that's the addition part. Yeah. Then, yeah, because we know we need large number of time units for the multiplication part, right? Yeah. Here, let's compare these two parts. Okay, addition part and the multiplication part. Yeah. How big is the difference? Yeah. Okay. All right. Yeah. Yeah. Because if you look at, so this is the total number of time units. Yeah. All right. Addition part, n is the addition part, right? Yeah. The multiplication part, 5n squared plus 5n. Can you see how large is their difference? Yeah. Quite large, right? Yeah. Especially when the number n is very large. Yeah. All right. And yeah, also another consideration, that's our assumption. The cost ratio between the unit cost of multiplication and the unit cost of addition is 10-to-1 ratio. Yeah, that's our assumption. Okay, all right. Yeah. So the question we want to answer here, yeah, which part do we have more room for improvement? Because we want to improve our method, the current algorithm. Yeah. And one way we can improve on this addition part. Another way we can put our focus on this multiplication part. Which way is better? That's my question. When you have limited resource, yeah, here let's assume our computing resource is quite limited. Yeah. So when we invest our precious computing resource, which part should we put our investment? Yeah. Addition part or multiplication part? Yeah. Two different parts. We can put our precious investment. Okay? All right. Yeah. That's the question. The answer is focus on the major part. The most common part. The largest portion of our total computation time. that is the multiplication part. Okay? Yeah. So let's summarize this idea here. The conclusion, yeah. Focus more on multiplications. We should put our effort, most of our effort, on improving this multiplication part. That's the conclusion. Okay, all right. Strategy, yeah, here. Based on this conclusion, so we set our strategy. Yeah. Reduce the number of multiplications. That's our next objective. Yeah? We set our next objective. This is next round objective. Yeah. All right. But the question, how to reduce the number of multiplications? Yeah? So we know which direction to go, right? Yeah. Reducing the number of multiplications. But the issue is we do not know how to do it. So we need to find the right way or a smart way to do that multiplication reduction step. Yeah. All right. Then, yeah, the smart method we will do here, B.3. It's called Horner's rule. Okay? Yeah. All right. Yeah. So before we finish this class, yeah, let me start. Yeah. One slide. Yeah. Let me do one slide. Yeah. In this Horner's rule. Yeah. Do some initial analysis. Yeah. So next time we will complete this smart, efficient algorithm, Horner's rule. Yeah. All right. Yeah. Now our goal, reduce the number of multiplications. Yeah. All right. Strategy. Yeah. So we need a strategy. Okay. Yeah. But this strategy, we used it before. Yeah. Yeah. So we are familiar with the strategy. So what's that? Study a simpler case. Yeah. Because we don't know how to do it, right? We have no idea. So we want to do some experiments. When we do experiments, we want to consider simpler cases. Certain simpler cases. That's the idea. Okay. All right. So let me try some simpler cases. Yeah. Do simple experiments. Discover certain property from the experiments. Yeah. All right. Yeah. It is easier to do experiments when the data sizes are small. Yeah. Here, there is a concept called a data size concept. So what's the data size concept? Yeah. Here, the number of coefficients is the data size. Yeah. That's our data, input data. The number of coefficients, that's the data size. Yeah. All right. When the data size is small, then the experiment is easier. Yeah. All right. Critical property. Yeah. Yeah. So here, when we do the experiments, we want to discover some critical property. Yeah. All right. So here, let's work, do some simple work here. All right. Let's consider our first experiment. We set n equals 2. N equals 2. Okay? Yeah. So that's this polynomial. Yeah. P2 of x equals, there are 3 terms in this polynomial. Yeah. So if you want to ask me why we do not consider n equals 0 and n equals 1, yeah. So the answer is, yeah, because there are 2 simpler cases, right? N equals 0 and 1, simpler than n equals 2. The answer also very simple. Because if we do experiments on these two simplest cases, then another problem we may have, that is, it's hard to discover the critical property. Remember? Our goal, we want to discover some critical property. If the data sizes are too small, then we have no chance to discover the critical property. So for that reason, we consider n equals 2, so we have a chance to discover some critical property. Okay. All right? Yeah. So let's try it. Yeah. Yeah. Then we need to really take some good observation on the terms here. Yeah. If you look at the last two terms, there is a very important property. That is, they have a common factor x. There is a common factor between the last two terms. Okay? All right? Yeah. So we should do something. Yeah. With this special property, we want to do something special here. Yeah. All right. Yeah. So let me show you some special operation we want to do here, factorization. We factor this common factor out. Yeah. All right. The left-hand side, the brute force method. Okay? So we do not do anything special on the left-hand side. Okay? But the right-hand side, we do factorization. Here you can see the forms are different. Yeah. We know both forms have the same number. Yeah. Same number. Yeah. We do not change the result number. Yeah. But they have two different forms. Yeah. So with two different forms, now let's do the counting. Yeah. If we count the number of multiplications from the left-hand side form, what's the number? 1 plus 2 equals 3. The first term gives 1 multiplication. Second, 2 multiplications. So you add them up, you have 3 multiplications. But now let's do the counting on the right-hand side form. X times this parenthesis, 1 multiplication. Okay? Yeah. Inside the parenthesis, A1, no multiplication. A2 times X, that's your second multiplication. So you add them up, you have 2 multiplications. You see the difference? Yeah. From 3 left-hand side form to using the right-hand side form. That's the improvement. Yeah. All right? Yeah. So our conclusion is when we apply the factorization operation, we can improve our algorithm by reducing the number of multiplications. Yeah. For this experiment, our gain is we improve the multiplication number from 3 to 2. Yeah. Yeah. It's, very encouraging. Yeah. Although you may feel the improvement is not that big, yeah, because our data size is small, right? Yeah. Think about when our data size becomes larger and larger, we may have much more improvement, right? Yeah. Yeah. So we will do next round, yeah, more improvement, yeah, in our next class. Yeah. So let's start our first half of part B. Yeah. Part B is pretty long. So the first half, yeah, we complete the first half of Power B today. Yeah. The next class, yeah, we try to complete the second half of Power B. Yeah. All right, so let me stop right here.